Okay. All right, so world history, 931. Finished first chapter, and then OpenStax world history down there. So I'm going to go ahead and do anatomy and physiology now. Uh, that'll get me caught up on yesterday, at least with the readings. And then I'm thinking, shoot. Um, maybe one or two workouts tonight before I go to bed. We'll see how that goes. And then maybe I'll do some transcriptions to get caught up on those. Seems like a good idea. All right. Okay. Anatomy, physiology. Chapter 1, an introduction to the human body. Oh, wait, I missed it. Hold on. Oh, no, that's right. Oh, they're doing it a little bit differently. Okay, so. Oh, that's chapter objectives. My bad. I got myself confused for a second. All right. Chapter objectives. After studying this chapter, you will be able to distinguish between anatomy and physiology and identify several branches of each, identify the structure of the body from simplest to most complex in terms of the 6 levels of organization, identify the functional characteristics of human life, identify the 4 requirements for human survival, define homeostasis and explain its importance to normal human functioning, use appropriate anatomical terminology to identify key body structures, body regions, and directions in the body, compare and contrast at least 4 medical imaging techniques in terms of their function and use in medicine. Introduction. Though you may approach a course in anatomy and physiology strictly as a requirement for your field of study, the knowledge you gain in this course will serve you well in many aspects of your life. An understanding of anatomy and physiology is not only fundamental to any career in the health professions, but it can also benefit your own health. Familiarity with the human body can help you make healthful choices and prompt you to take appropriate action when signs of illness arise. Your knowledge in this field will help you understand news about nutrition, medications, medical devices, and procedures, and help you understand the genetics or infectious diseases. At some point, everyone will have a problem with some aspect of their body, and your knowledge can help you be a better parent, spouse, partner, friend, colleague, or caregiver. This chapter begins with an overview of anatomy and physiology and a preview of the body regions and functions. It then covers the characteristics of life and how the body works to maintain stable conditions. It introduces a set of standard terms for body structures and for planes and positions in the body that will serve as a foundation for more comprehensive information covered later in the text. It ends with examples of medical imaging used to see inside the living body. 1.1 Overview of anatomy and physiology. Learning objectives. By the end of this section, you will be able to compare and contrast anatomy and physiology, including their specializations and methods of study, discuss the fundamental relationship between anatomy and physiology. Human anatomy is the scientific study of the body structures. Some of these structures are very small and can only be observed and analyzed with the assistance of a microscope. Other larger structures can readily be seen, manipulated, measured, and weighed. The word anatomy comes from the Greek root that means to cut apart. Human anatomy was first studied by observing the exterior of the body and observing the wounds of soldiers and other injuries. Later, physicians were allowed to dissect bodies of the dead to augment their knowledge. When a body is dissected, its structures are cut apart in order to observe their physical attributes and their relationships to one another. Dissection is still used in medical schools, anatomy courses, and in pathology labs. In order to observe structures in living people, however, a number of imaging techniques have been developed. These techniques allow clinicians to visualize structures inside the living body, such as cancerous tumor or a fractured bone. Like most scientific disciplines, anatomy has areas of specialization. Gross anatomy is the study of larger structures of the body, those visible without the aid of magnification. Macro means large, thus, gross anatomy is also referred to as macroscopic anatomy. In contrast, micro means small, and microscopic anatomy is the study of structures that can be observed only with the use of a microscope or other magnification device. Microscopic anatomy includes cytology, the study of cells, and histology, the study of tissues. As the technology of microscopes has advanced, anatomists have been able to observe smaller and smaller structures of the body, from slices of large structures like the heart to the three-dimensional structures of large molecules in the body. Anatomists take two general approaches to the study of the body structures: regional and systemic. Regional anatomy is the study of the interrelationships of all the structures in a specific body region, such as the abdomen. Studying regional anatomy helps us appreciate the interrelationships of body structures, such as how muscles, nerves, blood vessels, and other structures work together to serve a particular body region. In contrast, systemic anatomy is the study of the structures that make up a discrete body system, that is, a group of structures that work together to perform a unique body function. For example, a systemic anatomical study of the muscular system would consider all of the skeletal muscles of the body. Whereas anatomy is about structure, physiology is about function. Human physiology is the scientific study of the chemistry and physics of the structures of the body and the ways in which they work together to support the functions of life. Much of the study of physiology centers on the body's tendency toward homeostasis. Homeostasis is the state of steady internal conditions maintained by living things. The study of physiology certainly includes observation, both with the naked eye and with microscopes, as well as the manipulations and measurements. However, current advances in physiology usually depend on carefully designed laboratory experiments that reveal the functions of the many structures and chemical compounds that make up the human body. Like anatomists, physiologists typically specialize in a particular branch of physiology. For example, neurophysiology is the study of the brain, spinal cord, and nerves, and how these work together to perform functions as complex and diverse as vision, movement, and thinking. Physiologists may work from the organ level, exploring, for example, what different parts of the brain do, to the molecular level. Form is closely related to function in all living things. For example, a thin flap of your eyelid can snap down to clear away dust particles and almost instantaneously slide back up to allow you to see again. At the microscopic level, the arrangement and function of the nerves and muscles that serve the eyelid allow for its quick action and retreat. At a smaller level of analysis, the function of these nerves and muscles likewise relies on the interactions of specific molecules and ions. Even the three-dimensional structure of certain molecules is essential to their function. Your anatomy and physiology will make more sense if you continually relate the form of the structures you are studying to their function. In fact, it can be somewhat frustrating to attempt to study anatomy without an understanding of the physiology that a body structure supports. Imagine, for example, trying to appreciate the unique arrangement of the bones of the human hand if you had no conception of the function of the hand. Fortunately, your understanding of how the human hand manipulates tools, from pens to cell phones, helps you appreciate the unique alignment of the thumb in opposition to the four fingers, making your hand a structure that allows you to pinch and grasp objects and type text messages. Structural organization of the human body. 1.2. Structural organization of the human body. Learning objectives. By the end of this section, you will be able to describe the structure of the human body in terms of 6 levels of organization, list the level 11 organ systems of the body, and identify at least one organ and one major function of each. Before you begin to study the different structures and functions of the human body, it is helpful to consider its basic architecture, that is, how its smallest parts are assembled into larger structures. It is convenient to consider the structure of the body in terms of fundamental levels of organization that increase in complexity: subatomic particles, atoms, molecules, organelles, cells, tissues, organs, organ systems, organisms, and biosphere. The levels of organization. To study the chemical level of organization, scientists consider the simplest building blocks of matter: subatomic particles, atoms, and molecules. All matter in the universe is composed of one or more unique pure substance called elements, familiar examples of which are hydrogen, oxygen, carbon, nitrogen, calcium, and iron. The smallest unit of any of these pure substances is an atom. Atoms are made up of subatomic particles such as the proton, electron, and neutron. Two or more atoms combine to form a molecule. such as the water molecules, proteins, and sugars found in living things. Molecules are the chemical building blocks of all body structures. A cell is the smallest independently functioning unit of a living organism. Even bacteria, which are extremely small, independently living organisms, have a cellular structure. Each bacterium is a single cell. All living structures of human anatomy contain cells, and almost all functions of human physiology are performed in cells or are initiated by cells. A human cell typically consists of flexible membranes that enclose cytoplasm, a water based cellular fluid, together with a variety of tiny functioning units called organelles. In humans, as in all organisms, cells perform all functions of life. A tissue is a group of many similar cells, though that work together to perform a specific function. An organ is an anatomically distinct structure of the body composed of two or more tissue types. Each organ continues or performs one or more specific physiological functions. An organ system is a group of organs that work together to perform major functions or meet physiological needs of the body. This book covers 11 distinct organ systems in the human body. Assigning organs to organ systems can be imprecise, since organs that belong to one system can also have functions integral to the other system to another system. In fact, most organs contribute to more than one system. In this book, and throughout your studies of biological sciences, you will often read descriptions related to similarities and differences among biological structures, processes, and health related to a person's biological sex. People often use the words female and male to describe two different concepts: our sense of gender identity and our biological sex as determined by our chromosomes, hormones, organs, and other physical characteristics. For some people, gender identity is different from biological sex or their sex assigned at birth. Throughout this book, female and male refer to sex only, and the typical anatomy and physiology of XX and XY individuals is discussed. The organism level is the highest level of organization. An organism is a living being that has a cellular structure that can independently perform all physiological functions necessary for life. In multicellular organisms, including humans, all cells, tissues, organs, and organ systems of the body work together to maintain the life and health of the organism. 1.3 Functions of human life. Learning objectives. By the end of this section, you will be able to explain the importance of organization to the function of the human organism, distinguish between metabolism, anabolism, and catabolism, provide at least two examples of human responsiveness and human movement, compare and contrast growth, differentiation, and reproduction. These different organ systems each have different functions and therefore unique roles to perform in physiology. These many functions can be summarized in terms of a few that we might consider definitive of human life: organization, metabolism, responsiveness, movement, development, and reproduction. Organization. A human body consists of trillions of cells organized in a way that maintains distinct internal compartments. These compartments keep body cells separated from external environmental threats, and keep the cells moist and nourished. They also separate internal body fluids from the countless microorganisms that grow on body surfaces, including the lining of certain passageways that connect the outer surface of the body. The intestinal tract, for example, is home to more bacterial cells than the total of all human cells in the body. Yet these bacteria are outside the body and cannot be allowed to circulate freely inside the body. Cells, for example, have a cell membrane that keeps the intracellular environment, the fluids and organelles, separate from the extracellular environment. Blood vessels keep blood inside a closed circulatory system, and nerves and muscles are wrapped in connective tissue sheaths that separate them from surrounding structures. In the chest and abdomen, a variety of internal membranes keep major organs such as the lungs, heart, and kidneys separate from the others. The body's largest organ system is the integumentary system, which includes the skin and its associated structures such as hair and nails. The surface tissue of skin is a barrier that protects internal structures and fluids from potentially harmful microorganisms and other toxins. Metabolism. The first law of thermodynamics holds that energy can neither be created nor destroyed, it can only change form. Your basic function as an organism is to consume energy and molecules in the foods you eat, convert some of it into fuel for movement, sustain your body functions, and build and maintain your body structures. There are two types of reactions that accomplish this: anabolism and catabolism. Anabolism is the process whereby smaller, simpler molecules are combined into larger, more complex substances. Your body can assemble by utilizing energy, the complex chemicals it needs by combining small molecules derived from the foods you eat. Catabolism is the process by which larger, more complex substances are broken down into smaller, simpler molecules. Catabolism releases energy. The complex molecules found in foods are broken down so the body can use their parts to assemble the structures and substances needed for life. Taken together, these two processes are called metabolism. Metabolism is the sum of all anabolic and catabolic reactions that take place in the body. Both anabolism and catabolism offer simultaneously and continuously keep you alive. Every cell in your body makes use of a chemical compound, adenosine triphosphate, to store and release energy. The cell stores energy in the synthesis of ATP, then moves the ATP molecules to the location where energy is needed to fuel cellular activities. Then the ATP is broken down and a controlled amount of energy is released, which is used by the cell to perform a particular job. Responsiveness. Responsiveness is the ability of an organism to adjust to changes in its internal and external environments. An example of responsiveness is external stimuli. To external stimuli could include moving towards sources of food and water and away from perceived dangers. Changes in an organism's internal environment, such as increased body temperature, can cause the responses of sweating and the dilation of blood vessels in the skin in order to decrease body temperature, as shown by the runners in Figure 1.7. Movement. Human movement Human movement includes not only actions at the joints of the body, but also the motion of individual organs and even individual cells. As you read these words, red and white blood cells are moving throughout your body. Muscle cells are contracting and relaxing to maintain your posture and to focus your vision, and glands are secreting chemicals to regulate body functions. Your body is coordinating the action of entire muscle groups to enable you to move air into and out of your lungs, to push blood throughout your body, and to propel the food you have eaten through your digestive tract. Consciously, of course, you contract your skeletal muscles to move the bones of your skeleton to get from one place to another, and to carry out all of the activities of your daily life. Development, growth, and reproduction. Development is all of the changes the body goes through in life. Development includes the process of differentiation, in which unspecialized cells become specialized in structure and function to perform certain tasks in the body. Development also includes the processes of growth and repair, both of which involve cell differentiation. Growth is the increase in body size. Humans, like all multicellular organisms, grow by increasing the number of existing cells, increasing the amount of non-cellular material around cells, and, within very narrow limits, increasing the size of existing cells. Reproduction is the formation of a new organism from parent organisms. In humans, reproduction is carried out by the male and female reproductive systems. Because death will come to all complex organisms, without reproduction, the line of organisms would end. 1.4 Requirements for human life. Learning objectives. By the end of this section, you will be able to discuss the role of oxygen and nutrients in maintaining human survival, explain why extreme heat and extreme cold threaten human survival, explain how pressure exerted by gases and fluids influences human survival. Humans have been acclimating to life on Earth for at least the past 200,000 years. Earth and its atmosphere have provided us with air to breathe, water to drink, and food to eat. But these are not the only requirements for survival. Although you may rarely think about it, you also cannot live outside of a certain range of temperature and pressure that the surface of our planet and its atmosphere provides. The next sections explore these 4 requirements of life. Oxygen. Atmospheric air is only about 20% oxygen, but that oxygen is a key component of the chemical reactions that keep the body alive, including the reactions that produce ATP. Brain cells are especially sensitive to lack of oxygen because of their requirement for a high and steady production of ATP. Brain damage is likely within 5 minutes without oxygen, and death is likely within 10. Nutrients. A nutrient is a substance in foods and beverages that is essential to human survival. The 3 basic classes of nutrients are water, the energy-yielding and body-building nutrients, and the micronutrients. The most critical nutrient is water. Depending on the environmental temperature and our state of health, we may be able to survive for only a few days without water. The body's functional chemicals are dissolved and transported in water, and the chemical reaction of life that take place in water. Moreover, water is the largest component of cells, blood, and the fluid between cells. And water makes up about 70% of an adult's body mass. Water also helps regulate our internal temperature and cushions, protects, and lubricates joints and many other body structures. The energy-yielding nutrients are primarily carbohydrates and lipids, while proteins mainly supply the amino acids that are the building blocks of the body itself. You ingest these in plant and animal foods and beverages, and the digestive system breaks them down into molecules small enough to be absorbed. The breakdown products of carbohydrates and lipids can then be used in the metabolic process that convert them to ATP. Although you might feel as if you are starving after missing a single meal, you can survive without consuming the energy yielding nutrients for at least several weeks. Water and the energy yielding nutrients are also referred to as macronutrients because the body needs them in large amounts. In contrast, micronutrients are vitamins and minerals. These elements and compounds participate in many essential chemical reactions and processes, such as nerve impulses, and some, such as calcium, also contribute to the body structure. Your body can store some of the micronutrients in its tissues and draw on those reserves if you fail to consume them in your diet for a few days or weeks. Some other micronutrients, such as vitamin C and most of the B vitamins, are water soluble and cannot be stored, so you need to consume them every day or two. Narrow range of temperature. You have probably seen news stories about athletes who died of heat stroke or hikers who died of exposure to cold. Such deaths occur because the chemical reactions upon which the body depends can only take place within a narrow range of body temperature from just below to just above 37 degrees Celsius. When body temperature rises well above or drops well below normal, certain proteins that facilitate chemical reactions lose their normal structure and their ability to function, and the chemical reactions of metabolism cannot proceed. That said, the body can respond effectively to short-term exposure to heat or cold. One of the body's responses to heat, is sweating. As sweat evaporates from the skin, it removes some thermal energy from the body, cooling it. Adequate water is necessary to produce sweat, so adequate fluid intake is essential to balance that loss during the sweat response. Not surprisingly, the sweat response is much less effective in a humid environment because the air is already saturated with water. Thus, the sweat on the skin surface is not able to evaporate, and internal body temperature can get dangerously high. The body can also respond effectively to short-term exposure to cold. One response to cold is shivering, which is random muscle movement that generates heat. Another response is increased breakdown of stored energy to generate heat. When that energy reserve is depleted, however, and the core temperature begins to drop significantly, red blood cells will lose their ability to give up oxygen, denying the brain of this critical component of ATP production. This lack of oxygen can cause confusion, lethargy, and eventually loss of consciousness and death. The body responds to cold by reducing blood circulation to the extremities, the hands and feet, in order to prevent blood from cooling there and so that the body's core can stay warm. Even when core body temperature remains stable, however, tissues exposed to severe cold, especially the fingers and toes, can develop frostbite when blood flow to the extremities has been much reduced. This form of tissue damage can be permanent and lead to gangrene, requiring amputation of the affected region. Narrow range of atmospheric pressure. Pressure is a force exerted by a substance that is in contact with another substance. Atmospheric pressure is exerted by the mixture of gases in the Earth's atmosphere. Although you may not perceive it, atmospheric pressure is constantly pressing down on your body. This pressure keeps gases within your body, such as the gaseous nitrogen in body fluids, dissolved. If you were suddenly ejected from a spaceship from Earth's atmosphere, you would go from a situation of normal pressure to one of very low pressure. The pressure of the nitrogen gas in your blood would be much higher than the pressure of the nitrogen in space surrounding your body. As a result, the nitrogen gas in your blood would expand, forming bubbles that could block blood vessels and even cause cells to break apart. Atmospheric pressure does more than just keep blood gases dissolved. Your ability to breathe, that is, to take in oxygen and release carbon dioxide, also depends on precise atmospheric pressure. Altitude sickness occurs in part because the atmosphere at high altitudes exerts less pressure, reducing the exchange of these gases and causing shortness of breath, confusion, headache, lethargy, and nausea. Mountain climbers carry oxygen to reduce the effects of both low oxygen levels and low barometric pressure at higher altitudes. The dynamic pressure of body fluids is also important to human survival. For example, blood pressure, which is the pressure exerted by blood as it flows within blood vessels, must be great enough to enable the blood to reach all the body tissues, and yet low enough to ensure that the delicate blood vessels can withstand the friction and force of the pulsating flow of pressurized blood. 1.5 Homeostasis. Learning objectives. By the end of this section, you will be able to discuss the role of homeostasis in healthy functioning, contrast negative and positive feedback, giving one physiologic example of each mechanism. Maintaining homeostasis requires that the body continuously monitor its internal conditions. From body temperature to blood pressure to levels of certain nutrients, each physiological condition has a particular set point. A set point is the physiological value around which the normal range fluctuates. A normal range is the restricted set of values that is optimally healthful and stable. For example, the set point for normal human body temperature is approximately 37 Celsius. Physiological parameters such as body temperature and blood pressure tend to fluctuate within a normal range a few degrees above and below that point. Control centers in the brain and other parts of the body monitor and react to deviations from homeostasis using negative feedback. Negative feedback is a mechanism that reverses a deviation from the set point. Therefore, negative feedback maintains body parameters within their normal range. The maintenance of homeostasis by negative feedback goes on throughout the body at all times, and an understanding of negative feedback is thus fundamental to an understanding of human physiology. Negative feedback. A negative feedback system has three basic components. A sensor, also referred to as a receptor, is a component of a feedback system that monitors a physiological value. This value is reported to the control center. The control center is the component in a feedback system that compares the value to the normal range. If the value deviates too much from the set point, then the control center activates an effector. An effector is the component in a feedback system that causes a change to reverse the situation and return the value to the normal range. In order to set the system in motion, a stimulus must drive a physiological parameter beyond its normal range. This stimulus is heard by a specific sensor. For example, in the control of blood glucose, specific endocrine cells in the pancreas detect excess glucose in the bloodstream. These pancreatic beta cells respond to the increased level of blood glucose by releasing the hormone insulin into the bloodstream. The insulin signals skeletal muscle fibers, fat cells, and liver cells to take up excess glucose, removing it from the bloodstream. As glucose concentration in the bloodstream drops, the decrease in concentration, the actual negative feedback, is detected by pancreatic alpha cells, and insulin release stops. This prevents blood sugar levels from continuing to drop below the normal range. Humans have a similar temperature regulation feedback system that works by promoting either heat loss or heat gain. When the brain's temperature regulation center receives data from the sensors indicating that the body's temperature exceeds its normal range, it stimulates a cluster of brain cells referred to as the heat loss center. This stimulation has three major effects. Blood vessels in the skin begin to dilate, allowing more blood from the body core to flow to the surface of the skin, allowing the heat to radiate into the environment. As blood flow to the skin increases, sweat glands are activated to increase their output. As the sweat evaporates from the skin surface into the surrounding air, it takes heat with it. The depth of respiration increases, and a person may breathe through an open mouth instead of through the nasal passageways. This further increases heat loss from the lungs. In contrast, activation of the brain's heat gain center by exposure to cold reduces blood flow to the skin, and blood returning from the limbs is diverted into a network of deep veins. Oh, okay. So in contrast, activation of the brain's heat gain center by exposure to cold reduces blood flow to the skin, and blood returning from the limbs is diverted into a network of deep veins. Okay. This arrangement traps heat closer to the body core and restricts heat loss. If heat loss is severe, the brain triggers an increase in random signals to skeletal muscles, causing them to contract and produce shivering. The muscle contractions of shivering release heat while using ATP. The brain triggers the thyroid gland in the endocrine system to release thyroid hormone, which increases metabolic activity and heat production in cells throughout the body. So the cold therapy, so they're doing the cold shower, is actually a good thing. The brain also signals the adrenal glands to release epinephrine, a hormone that causes the breakdown of glycogen into glucose, which can be used as an energy source. The breakdown of glycogen into glucose also results in increased metabolism and heat production. So that's why I feel warmer. Positive feedback. Positive feedback intensifies a change in the body's physiological condition rather than reversing it. A deviation from the normal range results in more change, and the system moves farther away from the normal range. Positive feedback in the body is normal only when there is a definite endpoint. Childbirth and the body's response to blood loss are two examples of positive feedback loops that are normal but are activated only when needed. Childbirth at full term is an example of a situation in which the maintenance of the existing body state is not desired. Enormous changes in a person's body are required to expel the baby at the end of pregnancy, and the events of childbirth, once begun, must progress rapidly to a conclusion, or the life of the person giving birth, okay, so there are errors, and the baby are at risk. The extreme muscular work of labor and delivery are the result of a positive feedback system. The first contractions of labor push the baby toward the cervix. The cervix contains stretch-sensitive nerve cells that monitor the degree of stretching. These nerve cells send messages to the brain, which in turn cause the pituitary gland at the base of the brain to release the hormone oxytocin into the bloodstream. Oxytocin causes stronger contractions of the smooth muscles in the uterus, pushing the baby further down the birth canal. This causes even greater stretching of the cervix. The cycle of stretching, oxytocin release, and increasingly more forceful contraction stops only when the baby is born. At this point, the stretching of the cervix halts, stopping the release of oxytocin. A second example of positive feedback centers on reversing extreme blood damage to the body. Following a penetrating wound, the most immediate threat is excessive blood loss. Less blood circulating means reduced blood pressure and reduced perfusion to the brain and other vital organs. If perfusion is severely reduced, vital organs will shut down and the person will die. The body responds to this potential catastrophe by releasing substances in the injured blood vessel wall that begins the process of blood clotting. As each step of clotting occurs, it stimulates the region or release of more clotting substances. This accelerates the process of clotting and sealing off the damaged area. Clotting is contained in a local area based on a tightly controlled availability of clotting proteins. This is an adaptive life-saving cascade of events. 1.6 Anatomical terminology. By the end of this section, you will be able to demonstrate the anatomical position, describe the human body using directional and regional terms, identify three planes most commonly used in the study of anatomy, distinguish between the posterior and the anterior body cavities, identifying their subdivisions and representative organs around in each, describe serous membrane and explain its function. Anatomists and healthcare providers use terminology that can be bewildering to the uninitiated. However, the purpose of this language is not to confuse, but rather to increase precision and reduce medical errors. For example, is a scar above the wrist, located on the forearm 2 or 3 inches away from the hand, or is it at the base of the hand? Is it on the palm side or the back side? By using precise anatomical terminology, we eliminate ambiguity. Anatomical terms derive from ancient Greek and Latin words. Because these languages are no longer used in everyday conversation, the meaning of their words does not change. Anatomical terms are made up of roots, prefixes, and suffixes. The root of the term often refers to an organ, tissue, or condition, whereas the prefix or suffix often describes the root. For example, in the disorder hypertension, the prefix hyper means high or over, and the root word tension refers to the pressure, so the word hypertension refers to abnormally high blood pressure. Anatomical position. To further increase precision, anatomists standardize the way in which they view the body. Just as maps are normally oriented with north at the top, the standard body map, or anatomical position, is that of the body standing upright with the feet at the shoulder width and parallel, toes forward. The upper limbs are held out to each side, and the palms of the hand face forward. Using this standard position reduces confusion. It does not matter how the body being described is oriented. The terms are used as if it is an anatomical position. For example, a scar in the anterior carpal region would be present on the palm side of the wrist. The term anterior would be used even if the hands were palmed down on the table. A body that is lying down is described as either prone or supine. Prone describes a face-down orientation, and supine describes a face-up orientation. These terms are sometimes used in describing the position of the body during specific physical examinations or surgical procedures. Regional terms. The human body's numerous regions have specific terms to help increase precision. Notice that the term brachium or arm is reserved for the upper arm, and antebrachium or forearm is used rather than lower arm. Similarly, femur or thigh is correct, and leg or crus is reserved for the portion of the lower limb between the knee and the ankle. You will be able to describe the body's regions using the terms from the figure. Directional terms. Certain directional anatomical terms appear throughout this and any other anatomy textbook. These terms are essential for describing the relative locations of different body structures. For instance, an anatomist might describe one band of tissue as inferior to another, Or a physician might describe a tumor as superficial to a deeper body structure. Commit these terms to memory to avoid confusion when you are studying or describing locations of particular body parts. Anterior describes the front or direction toward the front of the body. The toes are anterior to the foot. Posterior describes the back or direction toward the back of the body. The popliteus is posterior to the patella. Superior describes the position above or higher than another part of the body proper. The orbits are superior to the oris. Anterior is ventral, posterior is dorsal, superior is cranial. Inferior is caudal, describes a position below or lower than another part of the body proper, near or toward the tail. The pelvis is inferior to the abdomen. Lateral describes the side or direction toward the side of the body. The thumb is lateral to the digits. Medial describes the middle direction toward the middle of the body. The hallux is the medial toe. Proximal describes the position in a limb that is nearer to the point of attachment or the trunk of the body. The brachium is proximal to the antebrachium. Distal describes a position in a limb that is farther from the point of attachment or the trunk of the body. The crus is distal from the femur. Superficial describes a position closer to the surface of the body. The skin is superficial to the bones. Deep describes a position further from the surface of the body. The brain is deep to the skull. Body planes. A section is a two-dimensional surface of a three-dimensional structure that has been cut. Modern medical imaging devices enable clinicians to obtain virtual sections of living bodies. We call these scans. Body scans and body sections and scans can be correctly interpreted. However, only if the viewer understands the plane along which the section was made. A plane is an imaginary two-dimensional surface that passes through the body. There are three planes commonly referred to in anatomy and medicine. The sagittal plane is the plane that divides the body or an organ vertically into right and left sides. If this vertical plane runs directly down the middle of the body, it is called the mid-sagittal or median plane. If it divides the body into unequal right and left sides, it is called the parasagittal plane, or less commonly, a longitudinal section. The frontal plane is the plane that divides the body or an organ into an anterior portion and a posterior portion. The frontal plane is often referred to as a coronal plane. The transverse plane is the plane that divides the body or organ horizontally into upper and lower portions. Transverse planes produce images referred to as cross sections. Body cavities and serous membranes. The body maintains its dorsal organization by means of membranes, sheaths, and other structures that separate compartments. The dorsal cavity and the ventral cavity are the largest body compartments. These cavities contain and protect delicate internal organs, and the ventral cavity allows for significant changes in the size and shape of the organs as they perform their functions. The lungs, heart, stomach, and intestines, for example, can expand and contract without distorting other tissues or disrupting the activity of nearby organs. Subdivisions of the posterior and anterior cavities. The posterior and anterior cavities are each subdivided into smaller cavities. In the posterior cavity, the cranial cavity houses the brain, and the spinal cavity encloses the spinal cord. Just as the brain and the spinal cord make up a continuous, uninterrupted structure, the cranial and spinal cavities that house them are also continuous. The brain and spinal cord are protected by the bones of the skull and vertebral column by the cerebrospinal fluid, a colorless fluid produced by the brain, which cushions the brain and spinal cord with the posterior cavity. The anterior cavity has two main subdivisions, the thoracic cavity and the abdominopelvic cavity. The thoracic cavity is the more superior division of the anterior cavity, and it is enclosed by the rib cage. The thoracic cavity contains the lungs and the heart, which is located in the mediastinum. The diaphragm forms the floor of the thoracic cavity and separates it from more inferior abdominopelvic cavity. The abdominopelvic cavity is the largest cavity in the body. Although no membrane physically divides the abdominopelvic cavity, it can be useful to distinguish between the abdominal cavity, the division that houses the digestive organs, and the pelvic cavity, the division that houses the organs of reproduction. Abdominal regions and quadrants. To promote clear communication, for instance, about the location of a patient's abdominal pain or suspicious mass, healthcare providers typically divide up the cavity into either 9 regions or 4 quadrants. The more detailed regional approach subdivides the cavity with one horizontal line immediately inferior to the ribs and one immediately superior to the pelvis, and 2 vertical lines drawn as if dropped from the midpoint of each clavicle. There are 9 resulting regions. The simpler quadrants approach, which is more commonly used in medicine, subdivides the cavity with one horizontal and one vertical line that intersect at the patient's umbilicus. Membranes of the interior body cavity. A serous membrane is one of the thin membranes that cover the walls and organs in the thoracic and abdominopelvic cavities. The parietal layers of the membranes line the walls of the body cavity. The visceral layer of the membrane covers the organs. Between the parietal and visceral layers is a very thin, fluid-filled serous space or cavity. There are three serous cavities and their associated membranes. The pleura is a serous membrane that encloses the pleural cavity. The pleural cavity surrounds the lungs. The pericardium is the serous membrane that encloses the pericardial cavity. The pericardial cavity surrounds the heart. The peritoneum is the serous membrane that encloses the peritoneal cavity. The peritoneal cavity surrounds several organs in the abdominopelvic cavity. The serous membranes form fluid-filled sacs or cavities that are meant to cushion and reduce friction on internal organs when they move, such as when the lungs inflate or the heart beats. Both the parietal and visceral serosa secrete the thin, slippery serous fluid contained or located within the serous cavities. The pleural cavity reduces friction between the lungs and the body wall. Likewise, the pericardial cavity reduces friction between the heart and the wall of the pericardium. The peritoneal cavity reduces friction between the abdominal and pelvic organs and the body wall. Therefore, serous membranes provide additional protection to the viscera they enclose by reducing friction that could lead to inflammation of the organs. 1.7 Medical Imaging. Learning Objectives. By the end of this section, you will be able to discuss the uses and drawbacks of X-ray imaging, identify 4 modern medical imaging techniques and how they are used. For thousands of years, fear of the dead and legal sanctions limited the ability of anatomists and physicians to study the internal structures of the human body. An inability to control bleeding, infection, and pain made surgeries infrequent, and those that were performed, such as wound suturing, amputations, tooth and tumor removals, skull drilling, and cesarean births, did not greatly advance knowledge about internal anatomy. Theories about the function of the body and about disease were therefore largely based on external observations and imagination. During the 14th and 15th centuries, however, the detailed and anatomical drawings of Italian artist and anatomist Leonardo da Vinci and Flemish anatomist Andreas Vesalius were published, and interest in human anatomy began to increase. Medical schools began to teach anatomy using human dissection, although some resorted to grave robbing to obtain corpses. Laws were eventually passed that enabled students to dissect the corpses of criminals and those who donated their bodies for research. Still, it was not until the late 19th century that medical researchers discovered non-surgical methods to look inside the living body. X-rays. German physicist Wilhelm Röntgen was experimenting with electrical current when he discovered a mysterious and invisible ray that would pass through his flesh but leave an outline of his bones on a screen coated with a metal component. In 1895, Röntgen made the first durable record of the internal parts of a living human, an X-ray image of his wife's hand. Scientists around the world quickly began their own experiments with X-rays, and by 1900, X-rays were widely used to detect a variety of injuries and diseases. In 1901, Röntgen was awarded the first Nobel Prize for Physics for the work in his field. The X-ray is a form of high-energy electromagnetic radiation with a short wavelength capable of penetrating solids and ionizing gases. As they are used in medicine, X-rays are emitted from an X-ray machine and directed toward a specially treated metallic plate placed behind the patient's body. The beam of radiation results in darkening of the X-ray plate. X-rays are slightly impeded by soft tissues, which show up as gray on the X-ray plate, whereas hard tissue, such as bone, largely blocks the rays, producing a light-toned shadow. Thus, X-rays are best used to visualize hard body structures such as teeth and bones. Like many forms of high-energy radiation, however, X-rays are capable of damaging cells and initiating changes that can lead to cancer. This danger and excessive exposure to X-rays was not fully appreciated for many years after their widespread use. Refinements and enhancements of X-ray techniques have continued throughout the 20th and 21st centuries. Although often supplanted by more sophisticated imaging techniques, the X-ray remains a workhorse in medical imaging, especially for viewing fractures and for dentistry. The disadvantage of irradiation to the patient and the operator is now attenuated by proper shielding and by limiting exposure. Modern medical imaging. X-rays can depict a two-dimensional image of a body region and only from a single angle. In contrast, more recent medical imaging techniques technologies produce data that is integrated and analyzed by computers to produce three-dimensional images or images that reveal aspects of body functioning. Computed tomography. Tomography refers to imaging by sections. Computed tomography is a non-invasive imaging technique that uses computers to analyze several cross-sectional X-rays in order to reveal minute details about structures in the body. The technique was invented in the 1970s and is based on the principle that as X-rays pass through the body, they are absorbed or reflected at different levels. In the technique, a patient lies on a motorized platform while a computerized axial tomography scanner rotates 360 degrees around the patient, taking X-ray images. A computer combines these images into a two-dimensional view of a scanned area or slice. Since 1970, the development of more powerful computers and more sophisticated software has made CT scanning routine for many types of diagnostic evaluations. It is especially useful for soft tissue scanning, such as of the brain and the thoracic and abdominal viscera. Its level of detail is so precise that it can allow physicians to measure the size of a mass down to a millimeter. The main disadvantage of CT scanning is that it exposes patients to a dose of radiation many times that higher than that of X-rays. In fact, children who undergo CT scans are at an increased risk of developing cancer, as are adults who have multiple CT scans. Jeez. Magnetic resonance imaging. Magnetic resonance imaging is a non-invasive medical imaging technique based on a phenomenon of nuclear physics discovered in the 1930s, in which matter exposed to magnetic fields and radio waves was found to emit radio signals. In 1970, a physician and researcher named Raymond Damadian noticed that malignant tissues gave off different signals than normal body tissue. He applied for a patent for the first MRI scanning device, which was in use clinically by the early 1980s. The early MRI scanners were crude, but advances in digital computing and electronics led to their advancement over any other technique for precise imaging, especially to discover tumors. MRI also has the major advantage of not exposing patients to radiation. Drawbacks of MRI scans include their much higher cost and patient discomfort with the procedure. The MRI scanner subjects the patient to such powerful electromagnets that the scan room must be shielded. The patient must be enclosed in a metal tube-like device for the duration of the scan, sometimes as long as 30 minutes, which can be uncomfortable and impractical for ill patients. The device is also so noisy, even with earplugs, patients can become anxious or even fearful. These problems have been overcome somewhat with the development of open MRI scanning, which does not require the patient to be entirely enclosed in the metal tube. Patients with iron-containing metallic implants cannot undergo MRI scanning because it can dislodge these implants. Functional MRIs, which detects the concentration of blood flow in certain parts of the body, are increasingly being used to study the activity in parts of the brain during various body activities. This has helped scientists learn more about the locations of different brain functions and more about brain abnormalities and disease. Positron emission tomography. Positron emission tomography is a medical imaging technique involving the use of so-called radiopharmaceuticals, substances that emit radiation that is short-lived and therefore relatively safe to administer to the body. Although the first PET scanner was introduced in 1961, it took 15 more years before the radiopharmaceuticals were combined with the technique and revolutionized its potential. The main advantage is that PET can illustrate physiologic activity, including nutrient metabolism and blood flow, of the organ or organs being targeted, whereas CT and MRI scans can only show static images. PET is widely used to diagnose a multitude of conditions such as heart disease, the spread of cancer, certain forms of infection, brain abnormalities, bone disease, and thyroid disease. Ultrasonography. Ultrasonography is an imaging technique that uses the transmission of high-frequency sound waves into the body to generate an echo signal that is converted by a computer into a real-time image of anatomy and physiology. Ultrasonography is the least invasive of all imaging techniques, and it is therefore used more freely in sensitive situations such as pregnancy. The technology was first developed in the 1940s and 1950s. So ultrasonography is used to study heart function, blood flow in the neck or extremities, certain conditions such as gallbladder disease and fetal growth and development. The main disadvantages of ultrasonography are that the image quality is heavily operator dependent and that is unable to penetrate bone and gas. And that's it for Anatomy and Physiology, Chapter 1.